the idea was that group of people made this measurement, and they measured it to be 240 microkelvin, which was what the theory said was the lowest temperature you could get.
I remember in the paper it even says, what is it, plus 200,
Plus 200 minus 60.
I have a question. Why is it asymmetrical?
Well, because that happens a lot, that your error bars are asymmetrical because of just the way in which the various contributions to your uncertainty come in. But it's hard to avoid thinking they knew the temperature couldn't be any lower than 240, so they didn't want to put a very, very low.
Just nailed it exactly as predicted by Doppler.
So we did the same thing a few years later.
And just kind of, in case someone's listening that doesn't know how this works, laser cooling fundamentally is just you get the atom to absorb. You're putting in a frequency that the atom absorbs only if it's moving towards the laser source. And then when it absorbs that momentum, so it slows down. But then when it emits into a random direction, and therefore net it's slowing down in the direction of its original movement.
Right.
So that's how that worked as well.
That's how what we call Doppler cooling.
Okay.
So
was that the principle behind the optical molasses as well?
Yeah, that's right. But it turns out optical molasses works even better than we had imagined, which we'll come to in a moment.
So there's like a secondary effect that wasn't expected, and that's where the extra cooling came from. That's
part of the extra cooling, and it makes
so it's not that the Doppler cooling was working better than expected. It's actually that there's an additional effect.
Something else going on. Okay. That's right, exactly. And right. So we did the same thing, and we were very, very careful. We tuned the lasers so as to produce the lowest possible temperature according to the theory. Mm-hmm. And we measured the temperature to be...
What does that mean to tune them? Like, what did you...
Well, so in order to do the process that you described, how do you get the atoms that are moving toward the laser to be absorbing from the laser that they're moving toward? Instead of, say, the atoms that are moving away from the laser, if they absorb, they'll speed up.
They're going to speed up.
Mm-hmm. So the way you do that is you make the frequency of the laser lower than the frequency that the atom wants to absorb if it were at rest. Mm-hmm. But the atoms are moving. So the Doppler shift, this laser beam is tuned a little bit below the frequency that the atoms would absorb if they're at rest. Then this atom moving toward the laser beam
sees a slightly higher
Doppler shift, sees a higher frequency, closer to the frequency it wants to absorb, and so it preferentially absorbs from this one compared to from this one. Mm-hmm. And it's that preferential absorption from the laser beams that oppose the motion of the atoms that leads to Doppler cooling. Now, we didn't talk about the heating, but you alluded to the fact that when the atom emits the light, it emits in random directions. So when you average over that, it doesn't do anything. But it heats the atoms. That is, a random addition of momentum is going to be a heating process. And there's also randomness in the absorption. Is when the atom is sitting with all these laser beams coming in from all these directions, it's random which laser beam it's going to absorb from. It's not equal probability, because that will depend on the Doppler shift. But there's still an element of randomness, and that element of randomness also adds to the heating. So you balance the heating and the cooling. I can do that derivation in just a few minutes, which I do for students, but I won't do here. And you get the temperature. 240 microkelvin. So we did it in our lab. 240 microkelvin. We did it exactly the same way Steve Chu did it, but we thought we were being even more careful. We tuned the laser to just the right frequency to make the temperature minimum 240 microkelvin. And then we started to do more experiments because, you got a new thing. Let's do some more experiments. What will happen if we increase the intensity of one of the laser beams? Well, it should push the atoms out. And we could calculate how fast it should push the atoms out. Didn't work. That is, it was much less of an effect than what we had calculated. Change the detuning of the laser. We'd started off with it being optimal. Make it bigger. That should make it hotter. Well, we weren't measuring the temperature. We were just measuring how long it took the atoms to get out, because it was so much easier to do that. Measuring the temperature was really, really hard. That was why it's such a big uncertainty. Okay? So we said, let's measure the things that are easy. you've heard the joke about, looking for your keys under where the lamppost is, right? Well, it was a lot easier to measure the how long it took the atoms to get out of the molasses than it was to measure the temperature. So that's what we were measuring. And we calculated what kind of effect that should have. Didn't have that effect. So we were confused. We're doing all these measurements for something we thought we understood, and it wasn't giving the results. So finally, one of my colleagues, Paulette, says, look, we measured the temperature, but we did a slipshod job because it's so hard. What if we really measure the temperature really well? Maybe we'll learn something about what's going on here.
Did anyone else, like other groups, except the Stephen Chu experiment, did other people try to remeasure the temperature?
Not yet, because it wasn't hardly anybody working on this. Okay, so this was early days, and people weren't really working on it. I think the group out in Colorado was probably Carl Wyman's group was also measuring with cesium. By this time, we got diode lasers, and diode lasers made it possible to do cesium, and he was getting the Doppler limit for cesium. Okay, so everybody's getting the Doppler limit.
Also, like for Stephen Chu, like his experiment of 1985. So was it like a dead end? So he measured it. All right, everything agrees. That's it.
No.
People tried to.
They were going on. They
it?
were going in a wonderful direction. They were developing laser trapping. They were making what we now would call an optical tweezer, and focusing a laser beam into the molasses and trapping the atoms. No, they weren't sitting around. Okay, people were doing stuff. They were doing different stuff. So anyway, we decided let's measure the temperature really well. So we decided the way we would do that is we'd start with the molasses, with all laser beams coming on, do just like before, turn the laser beams off, so now the atoms expand. And let's put another laser out here. So the atoms will take a certain amount of time to get there. And when they do, they'll light up, and we can measure the time it takes. So if the atoms are really hot, then it'll take less time than if they're going slowly. So we did that. Atoms here, another laser beam up here. We saw nothing. 0 atoms here. And everything was working the way it was, the way it should.
No matter how long you waited.
No matter how long we waited. Well, I mean, after a little while, you don't expect there to be any atoms left. So no matter how long we waited, they weren't there. We checked to make sure everything was working the way it should, pushed the atoms up, to make sure that our detector was working the way it should. Everything's fine. And then we said, what if we put the laser underneath the atoms? Big signal. The atoms were going so slowly, they couldn't make it up. They couldn't get up to where we put the laser. Just gravity. Wow. We'd done the calculation. Gravity shouldn't have had any effect at all. At the temperature we thought, the atoms couldn't be any colder than that. So then we put the thing down here, boom, big signal. And we just measured it, 40 microkelvin. 6 times lower temperature than what was predicted, which was 240. So we were scared. We thought, we're obviously doing something wrong. This can't be true. In fact, I remember months earlier, I had gone to one of the theorists who worked on laser cold, and I said, look, we're seeing all these strange results. We don't know what's going on. We can't explain it using a 2-level atom. I probably didn't even say that. I said, we can't explain it using any of the techniques that we use. In fact, I had gone the summer before to Paris and spent a month in Paris working with Jean Dalibard and Claude Cohen, trying to figure out if we could determine what was going on. And they were experts at doing things, our effects of high laser intensity coming in, something we couldn't figure anything out. I went to a conference that summer, presented the results, said, people, tell us what's happening. Okay.
This is very rare these days, I guess. You show up in the conference like, look, it doesn't work. Explain, help me.
Yeah, I went to one of the theorists and I said, look, we got all these results we don't understand. If the temperature were a lot lower then what the theory says is possible. Maybe some of this might make sense. He said, no, that's not possible. There's no way the temperature could be lower because there's only one characteristic energy in the problem. That's the line width. That's the thing that sets the temperature, and that's it. I said, okay. So then we measured the temperature, and it's 6 times lower. Not like 10% lower, 6 times lower. So we're scared because everybody knows that you can't have a temperature that low. So we decided, okay, we will first check out the thing we were doing. Everything checked out. We found that if we increased the detuning of the laser, made it further from resonance, which is supposed to make the temperature hotter, it made the temperature colder. Then we said, okay, we're doing something wrong. Let's figure out another way of measuring the temperature. And so we went back to the old way.
So did you adjust, so there's like the velocity distribution, so the detuning originally, you would aim for the maximum of this kind of velocity distribution?
No, we wouldn't aim for the maximum velocity distribution. We would aim for the detuning from resonance that would maximize the force. Almost. It's, because of the way the heating and the cooling go together, the place that maximizes the force is not the same as the one that minimizes the temperature, but it's almost the same. So we did that so as to minimize the temperature, which is almost the same as maximizing the force. And it turns out, now we know, that isn't the place that minimizes the temperature. That's the place that minimizes the temperature for Doppler cooling, but not for the new kind of cooling that we accidentally discovered. So what we did was we developed 4 total different methods of measuring the temperature. The old way, what I called release and recapture, except we really took care of all the uncertainties. So in the past, we didn't take into account what the shape of the laser beam was, what the shape of the atomic cloud was. This time we did. And we took into account the fact that the atoms were falling, which the old theory didn't take into account because it didn't matter. It was such a small effect given the atoms at 240 microkelvin. The fact that gravity just didn't matter. But now we figured we better take it into account. We figured use gravity. Put the thing above, move it down until we start to see atoms. See how many atoms that get there as a function of how high it is. And when we had all 4 methods were showing that the temperature was way below the Doppler limit, then we published. And then other people went into their labs and were more careful and found out that, yes, the temperature was lower.
How was the mechanism elucidated?
So when we decided we really knew what we were doing, we called up our friends in Paris, Jean Dalibard and Claude Cohen-Tanucci, and said, look, we've measured the temperature. We're sure. We measured it lots of different ways. We are positive the temperature is way lower. What's going on? Well, they were so well placed, theoretically, to answer that question because they had already figured out a different cooling mechanism that happened when you use really strong laser beams and tune it to the other side of resonance. There was something that would happen that they had dubbed Sisyphus cooling. And now they realized that a similar thing could happen if you tune below resonance the way everybody does at low intensity because of the fact that the atoms were not 2-level atoms. You see, the trouble was that all this theory that I've been talking about was based on an underlying assumption that there's one ground state and one excited state. The laser takes you from that single ground state to that single excited state, and it decays back down to that ground state. The fact of the matter is that we were working at the F equals 2 level of the hyperfine manifold of the ground states. There's 5 different magnetic sublevels and a whole bundle upstairs, 7 different sublevels. And we thought we knew that, of course. It's just that we thought it didn't make any difference. Why? Because the only thing that determines the temperature in the Doppler cooling theory is the line width. And the line width is the same for all the different transitions. So we thought, since alignment is the only thing that determines the temperature, it's going to not matter that we've got all these different transitions. That was wrong, because it left out all kinds of other wonderful things that happen that we just were ignoring, and that Dalibard and Tanucci figured out. And that is, among the things, is that when you put the light on, it shifts the energies of the different states. This is called the light shift. Tanucci discovered the light shift for his thesis way back in whatever it was. That's an interesting story as well. This is before lasers.
Could it be somehow related, like, to Stark effect in terms of
It
like,
is.
shifting
It is.
the levels in the electromagnetic field?
In fact, today we call it the AC Stark effect.
Mm-hmm.
So it's very much like the Stark effect. It's applying an electric field, shifts the energy levels. But because there's different strengths of coupling between the ground state and the excited state for the different levels, then you get a different shift for the different levels. But that's not all. When you interfere two laser beams that have different polarizations, then the standing wave that's created when you interfere those laser beams will have what we call a polarization gradient. That is, when we sum the two fields together and they have different polarizations, they will sum to something whose polarization changes as you move in space, changes over a very tiny distance, a fraction of a wavelength.
Were you aware of that in your experiments when you would send a laser beam? I don't know. Did you put was it a mirror or two?
No, it was all accidental.
Laser?
No, we just used straight mirrors. So we did not change the polarization. But in 3D, you cannot make all the polarizations in the same direction because light is transverse. So if I have two laser beams propagating in this direction, they could be polarized like this, horizontally. And I could have another two laser beams, and they could also be polarized horizontally. When they interfere, it's all going to be horizontal. But now, when I bring in a laser from the other direction, then it can't be in the same direction. It's got to be, or it can be horizontal, but it's got to be in a different direction, because it can't be.
So I probably did the polarized in its own direction of motion.
Right. So let me do this again. Two laser beams polarized like that. Another two laser beams polarized like that. The one coming down cannot be polarized this way.
Right.
Mm-hmm.
Okay. It has to be polarized like this or like that, and that's going to interfere with the other ones to produce this thing that we call a polarization gradient.
So the fact that the laser beam has a thickness means that they create these like wherever they overlap, there's like a non-zero thickness where there's this polarization gradient.
But they're overlapping over everywhere that we want to do the experiment. Right. So it's not like they happen to overlap. That was something that was built into the experiment. They should
it's
overlap.
like no matter how do you try, you're gonna have this polarization gradient.
That's right, exactly. So now we do it deliberately, but back then it was just accidental. And so now what that means is that the different sublevels will be shifted differently by the light in a way that changes as you move through space.